So, in this section, I will talk a bit more about the images and deep learning over images. I will focus more on the use cases than on detailed descriptions about the methods itself. Maybe I will mention some really fundamental ideas, a few of them, but generally I would like to show you more the examples and practical usage of deep learning over images. But before we will jump in, I would like to go back in 2012, where it actually everything started for deep learning over images when Alex Kryzewski, who was student of Jeffrey Hinton on Stanford, has quite good idea to revisit one of the old ideas of Jan LeCun, who is currently, I believe, the head of research in Facebook. And Jan was working really back in times in like 1998 on some idea how to process the numbers from registration plates, and he brought the idea of convolution neural networks. And Alex Kryzewski actually revisited this idea, and the only thing he did is he took the architecture and put it on GPU and tried to train this architecture on ImageNet, which is big data set of images. And the task is to classify those images in 1,000 categories, and you can compete in a competition, in classification competition. So Alex did this. He trained so-called AlexNet, which was actually the LeCun's net trained on GPU, and took part in this competition, and he actually won. And he won by a huge margin back in time. And all other methods were more like classical methods. It was for the first time that neural network won that kind of competition. And from that time until now, all the time was the winner, the convolution neural network. And so you can see his architecture. So each square here is one layer, and you can see many times the conv layer, what it actually is. I think it's one most important fundamental idea which caused that deep learning on images is nowadays like a major approach how to process the images. So let's have a look on this. We can think about the image as about tensor. So it has three channels, red, green, and blue, and it has special properties, so height and width. And if you would like to process it with a feed-forward network, which Jirka showed you, you would probably use some matrix which would make a transformation of all the pixels and apply some nonlinearity and get the output in one neuron. And this approach would basically ignore all the spatial properties which are encoded in the image. So the idea of a convolution layer is to use something which is called convolution filter. And you can think about this as a small matrix which can traverse across the image. And you can think about this matrix as about an eye which is looking to the image and searching one concrete pattern, for example, the horizontal line. And this eye is traversing through the image and basically builds kind of a heat map of this feature. And you can have multiple eyes. So we had the green eye, which, for example, was searching the horizontal line, and then there is a red eye, which searches something different, like circles in the image. And you can have really multiple eyes which are applied to the image, and the output would be actually another image which has not three channels but 4 channels. It has again some width and height, and encodes what those eyes see in the image. And actually, you can see that the number of weights, the number of parameters which you need to learn is pretty small, because the matrices are actually pretty small. And when you train the neural network, what do you actually, I've forgotten that this output of one convolution layer can be applied again can be input to another convolution layer in the next layer of deep neural network. So then you can use another eye, and this eye would look on four channel image, and again it would search there some high level patterns. And when you train this type of architecture, and you would be interested in what's actually happened during the training. During the training, you were adjusting the eye to search something meaningful, because in the beginning, those filters which traverse across the image are just initialized by something which doesn't make much sense. But during the training, actually in the filters, through the filters you will be able to find some meaningful things, and you can also visualize it. So when you would look into the trained neural network, for example, to the first layer, you will find out probably that those eyes are searching for some really basic patterns, like diagonals of many colors. So this is the visualization of the filter, and these are actual inputs from the image which triggered this eye when it saw what it was searching for. And when you would go into the upper layers, you will suddenly realize that in the upper layers, the convolution filters, those eyes, are searching for more complex patterns in the image. It's just the whole field which is interested in visualization of those things, because it's not such trivial to visualize specifically what convolution filters in upper layers of those neural networks are searching for, because you cannot just visualize the matrix, because the input to the matrix is previous layer, which is not like normal image. It's some transformation already. So it's not trivial, but when we apply methods how to visualize this, we can see that, for example, in really upper layers, the convolutional filters search entities like people. And it's pretty much the similar way how your brain, your cortex is working when there are really layers of neurons, and some neurons are triggered by really simple visual stuff like light or dark, and some layers which are like more backward are triggered by entities like some neurons are triggered when you see your sibling or your mother or just random person, and it works pretty much similar in those architectures. But the most interesting and important thing for deep learning over images and those findings is that we can extract again something which is called embedding, similarly as Jirka showed you with the word2vec. When you have some representation of words encoded into constant size vector, you can do this also with deep neural networks over the images. And the cool thing is that actually the image itself, when you think about it as a row of pixels, it's really unstructured information in a way that if you would just make a row of the pixels and you would just pick one of the pixels, it doesn't tell you much. It would have some color, but actually you need some neighborhood around that pixel to make some reasoning around it. But if you have this embedding, which is actually constant size embedding, like 30 numbers, each number has its own meaning, own semantic, and basically encodes the key information which are in the image, like what objects are there, where are those objects, what is the style of the image. So I will show you in the following examples how it works. And we actually basically use those embeddings for all other more complicated tasks, which are basically built on those pre-trained neural networks, which are trained in those classification tasks. So first chapter of my talk would be dedicated to classification, and we started with ImageNet in like 2012, and each year of the competition, people came with basically deeper neural network and deeper neural network. So that was one trend. Another trend was that they realized that better is to use smaller convolution filters, because those so-called eyes are focused on more details. So they started to use small convolution filters, and then they started to use much more tricks, which I won't talk about now, but maybe after the talk. And basically, the community started to follow like three interesting paths. One path was how to make this convolution neural networks smaller to be able to put them on mobile devices and keep the performance. One path is really to focus on high performance in those classification tasks, so making predictions as accurate as possible. And third is making predictions fast, because you, for example, want to process video in a live, so you need this neural network to be fast. I will show you some pre-trained neural networks in this chart. So on x-axis, there is a number of operations you need to do for the prediction. So lower number, better. And on y-axis, there is an accuracy. And it's pretty old image. So this is kind of, I would say, obsolete, but the sweet spot is here in the top left corner. Here is, for example, ResNet 50, which is trained by, I believe, Microsoft. So all those neural networks are actually trained by those third-party providers like Facebook, Google, Microsoft. The reason why it is so is because it costs a lot of money to really train those convolution neural networks, this big architecture, to have this kind of performance. Because you need really like millions of images, and it takes like weeks to train those neural networks. But the good thing is that all of those guys are like publicly for download, and you can really download this pre-trained neural network and, for example, adjust it by fine-tuning, which means adjusting of the embedding a little bit for your classification task, or you can use for another task I will be talking about. These days, there are some other approaches which has much better results than those guys here. And the main reason why these networks are better is that the architecture is generated in automated way. So, for example, NASNet, the architecture wasn't designed by people, but they use recurrent neural networks to really build the architecture, and they trained the neural network, and they got like really awesome results. And not only in classification tasks, but they used the similar neural network, pre-trained neural network, for other tasks like object detection and stuff like this. And in all those tasks, this neural network actually won back in time. And the second thing which we realized, if we want to make neural network over images better, it's not enough to just make a neural network deeper. We need to also make the embedding wider. And at the same time, we need to have a high resolution bigger resolution of the images. So, for example, this, which I believe the EfficientNet is these days kind of state of the art. Maybe there are some better ones, but definitely a few months ago it was the state of the art. So these guys actually were focusing on scaling in the neural network in the right way. So they make it deeper, but also the embedding was wider, and they used bigger resolution of the input, and it really helped to get where they are in the top left corner. Okay, so this is the most basic task of classification. All other use cases I will show you basically build on those pre-trained neural networks and try to add some extra layers to the top of the neural network to do the specific task. One of the specific tasks is object detection. The output of the object detection neural network could look like this. So it really draw the squares around some objects and try to classify what the object is. And the way how it's actually trained is very interesting. So you cover whole image by those rectangles. It's deterministic how it's covered. Those rectangles are called anchors. And you actually train neural network to pick anchors which should cover your true label, which is here, the annotation, and then you train the neural network to adjust this anchor to really fit the label, which is this kind of square. And this work is actually done by Ross Grishik, and I remember like 2 or 3 or 4 years maybe ago when he was publishing those papers about fast and faster RCNN, region proposal convolution neural networks. And we were re-implementing his work, and actually we thought, okay, we re-implemented everything, and damn it doesn't work. And the catch for us was really simple. We didn't use high-resolution images. So when we use another data set which contained high-resolution images, we actually reproduce these results. So I always thinking, my God, how many researchers were so close to some breakthrough and they just didn't pick like right resolution images, and fuck, didn't work, and they just left the idea, and idea was right. And it's actually the similar with Jan LeCun. Actually, he had his neural network in 1998, but there was not boom of deep learning in 1998, and you can ask yourself like why we don't have those all great ideas already like 20 years here. And there are multiple reasons. One of them is GPU. He probably didn't have like this computation power in 1998. But you can see that in contrast with a text, here you need a lot of people who will prepare your data set, because you need some good annotation. In classification tasks, if you have a million of images, somebody needs to tell what is on the image actually. So I don't believe that in 1998 Jan LeCun even have like possibility to get to those type of data sets. And for example, for this classification task, somebody really need to prepare those rectangles before you will train your neural network which would draw those rectangles. So these days we have like MS-COCO dataset or Visual Genome. These are like nice data sets to use, and I believe that these are a few reasons why actually the boom happened in 2012, not in 1998. So this is the object detection. If we will step a little bit further, there is a semantic segmentation idea. So this idea is not about drawing the rectangle, but pixel by pixel, like identifying the entities in the image. And the architecture is pretty simple. So you will take the convolution neural network and end up this convolution neural network with kind of inverse convolution network. So suddenly you really produce pixel by pixel prediction of the color, and each color represents some entity you are searching in the image. And the hardest part again is to prepare the data set for you, because you need somebody who will actually do this work for you on a reasonable amount of images to enable you to train the neural networks to do those things. So it's like supervised training. And the combination of two approaches of the object detection and semantic segmentation is called instance semantic segmentation. The difference is that now you can detect the objects. For example, here is object probably person, but you can also identify each instance of this object. So it's kind of combination. Generally, object detection is a really widely used use case in industry. People use it in automated lines for robots, which just picking, for example, some like crappy stuff which goes on the line instead of people. And you can see it, for example, in self-driving cars, because those approaches help to detect the lines on the road, or like traffic signs, pedestrians, stuff like this. So it's really heavily used use case in the industry. These days, people mostly focus definitely on accuracy, but also on speed, because all the use cases usually happens in a real time. So you want to be able to do the predictions in a real time somehow. Then we have, I will jump to the next big topic, which is combination of convolution neural networks with really other domains. And Jirka was already talking about text generation. But what you can do, you can use an image as a source information and start to generate some text describing what is on the image. Here are some examples of the predictions which went great. So a person riding a motorcycle on a dirt road makes sense. Here you can see that there are 3 dogs instead of 2, and sometimes it's just predicting nonsenses. The idea of how it works actually is pretty simple. What you would do is you would use, again, pre-trained convolution neural network to extract the embedding, this vector of information, and you will use it as a seed information to recurrent neural network, which already Jirka shown you how it works. And this information can basically influence what would be generated on a way. And again, you need like really good data set for training. So somebody really needs to write those things for some training images, and then you are able to really train this end-to-end architecture. Extra step further in text generation is about attention. So you can have, again, this text generator, bird is flying over a body of water, but instead of like extracting the embedding from original image and then let the generative model generate the text, you can have attention module, which basically look to the image through the attention every time it generates next word, and you can really have a look where the model is looking during the generation of the text. So when the model is talking about the water, it actually focuses on a part of image where the water is, and when it talks about the bird, I believe it sometimes somehow points to the bird. It's nice because when you have some false positives or like crappy working model, you can have a look what makes the confusion through the attention. So you will use the attention and have a look, okay, this is pretty much understandable because model is confused because of something. Okay, then we have some more artistic things related to image processing. Maybe you saw something on your Twitter or whatever, because it's always like good topic. So one of really classical examples proposed by Justin Johnson from Stanford is style transfer. And again, it's built on the idea of the embedding. So what we have here? We have here some source image of the car, and then we have the image of some painting, and you would like to transfer this style of this painting to the image. So what you can actually do, you can have a look on the embedding which represents your image, and the embedding which represents the painting. And actually in the embedding of the painting there is encoded the style. So you can try to adjust, basically by backpropagation, the image in a way that those embeddings of the painting and your image are getting closer together. I'm a little bit simplifying, but this is the core idea of the paper. And you can get to really amazing results. Again, a lot of work behind this, but I can give you some nice links also to Google Colabs, where you can really run it into your browser with your images, and it's really out of box. Last part of my talk would be dedicated to another idea. Until now, we mostly talk about kind of task which had as an input the image, and the output was something else. Now we will change it, and the output of the model would be image itself. And I will be talking about generative adversarial networks. Here is a nice example of the output of those models. So here we have a model which basically generates the faces of the people, and you can see the progression during time. These days in 2020, we have pretty much photorealistic faces generated by those models. It's 2018, so these days it's much better. Major improvement happened actually with the background, not with the faces itself, because it was really hard for generative models to somehow grasp the background, because it was not so consistent, but the faces are pretty much consistent in a way how it looks like. And I would like to tell you the basic idea of generative adversarial networks, because it's nice. So basically, when we train these generative models, we actually have two models. One we have here, it's kind of, I would say, policeman, which input is the image, and this policeman should say if the image is fake, which means it's generated, or it's real. So it's from like a picture of normal real person. And the input to this policeman, to this discriminator, is either output from your generative model, which tries to generate some realistic face, and another input is the real face. And the training goes into two phases. First phase is that you really freeze this generator in a state where it is, and you will let it predict, you will let it generate some faces and take some real faces, and you will try to improve the discriminator to be better to detecting fake and real images. And then you will change it, you will fix the discriminator, and try to improve this generator to generate better faces. You mean maybe you are wondering what is this here? It's random noise as an input. What it actually means? And it's interesting. So this so I will talk a little bit about this. So this random noise is usually some random sample from multivariate Gaussian, so from multivariate normal distribution. And the reason why it is so is that when you look on the images of faces, basically everything on your face is normally distributed. So for example, if people are smiling or not, it's usually normally distributed, because this is like normal thing. This is really on the tail of the normal distribution. The same is with the size of your ears, the color of your eyes, the length of your hairs. So basically, with this this random noise, this latent vector, which is the input, you encode those attributes, and the generative model will try to match it to like real face. So this is, I mean, when I saw it for the first time, I was really wondering why it's like random noise. So this is why it is. But the input to the generative model don't need to be only the random noise for generating the face. Another nice example is making the blurred images sharper. So the input to the generative model is the blurred image, and you can try with generative model to sharpen it. Or you can use black and white image as an input, and the task is to make the image colorful. The nice thing about generative models is that usually you can generate your dataset by yourself without any need for annotations, because you can easily take a lot of colorful images from internet and convert it to grayscale, and then try to train the generator to really add the colors back. So it's a nice thing. And with the generative adversarial networks, I would like to end up my talk with the adversarial attacks and basically abuse of those methods, because generally images and deep learning over images is implemented everywhere, like in industry, in self-driving cars, on internet, in your e-shop, or whatever it is, in your mobile phone. And until now, not too many people were thinking about the fact if it could be dangerous, and what are dangers. So I have one alternative for you for a GPT-2 case, which was Jirka talking about, when the GPT-2 generated some text and people cannot recognize if it was generated by a person or by a machine. And we have kind of similar example with the generative models, because we can not only generate the face, but we can manipulate with the face. So you can, for example, simulate that the face is talking. And I'm not sure if you know quite famous example with Barack Obama, who was actually talking, but it was not him, but it was the generative model which was modifying his mouth. So it was really hard to recognize if it's fake or not, at least for the first sight. And people don't know about it too much, because we are used to, when we saw something in a video, it must be true, because we are not used to that there exist such methods to make those kind of attacks. And the last example I would like to show is back from the classification tasks and object detection tasks. I already tell you that self-driving cars are using a lot of deep learning in their engines, and nowadays it's quite popular to try to create adversarial attacks, which are those small stickers which are on this traffic sign stop. And when this neural network look at it, it thinks, in this concrete example, I think that speeding limit is 60 or something like this. So it interprets it completely different than a stop sign. But at the same time, like human is not able to recognize that this is kind of adversarial attack. And I mean, this would be definitely one of the open topics for like next year, maybe next years, how we can like tackle this problem, because you don't want to somebody who will just go in front of your car on a highway and just show some image to your camera in your Tesla, and your Tesla will just go out of the road and it will kill you or something like this. So these are the open topics, maybe good for discussion at the end of our session. And this is all from my side. Now I believe we will have a little bit rest, because you must be dying. And I should also remind you that there is what should I remind? Yeah, next slide. Here we go. That you have some discount, and we would like you, if you could vote for a talk you would like to hear the most, or the lecture from our side. So if you could vote, it would be awesome. Marek, come here to me.
Thank you, Adam.